All right, I'm going to start with this doc because it's a pretty good overview um, of why all of this works. So the underlying problem is that with Rados, when you write, you have to touch all the replicas, and so writes always ensure that everybody is like in not technically quorum, but whatever, everybody agrees there's no split brain. But on reads, you're only reading from the primary, which is normally fine. Because usually either the primary is still the primary or the primary has seen an OSD map that says it's not the primary, so it knows that it's not the primary, and so it'll ignore the read request. But it's possible that you could have a network partition so that you've partitioned off the primary, and it doesn't realize that the cluster has moved on and somebody else is now primary and is doing something else. So the OSD doesn't know that yet, and a client could still be reading from it. It's pretty hard to trigger that case because you have to sort of partition that OSD off from the rest of the cluster and the client also, and the client to be reading from that. But it can happen. There's the test, there's a sort of a unit functional whatever test that does it basically by blacklisting connections between certain OSDs and clients and having two Rados clients and whatever. It induces a situation where you have a stale read, where you've written to the remaining replicas, but this other client can still read the old value from the old replica. So this has been around for a long time. It was finally fixed. I think we discovered it like around Firefox or something like that, but it took a long time to actually fixing it because it's but around Octopus?
Yeah, Octopus.
Octopus, we finally merged the fix. So basically we do this by adding read leases. So the key thing is that there's sort of a read lease interval property. It's an optional pool property that you can specify on a per pool basis. So you can define how long this is. But by default, it's not set on a per pool. And instead, we use this global config option read lease ratio. And it just multiplies that times the heartbeat grace. So the idea is basically that the read leases will always be shorter than the heartbeat grace. And so if we ever have an OSD go down and it fails a bunch of heartbeats, by the time we've actually decided to mark that OSD down, the read leases will have already expired. And so we won't actually notice the fact that there's this like read lease mechanism that is happening. It'll sort of be hidden by other delays already in the system. And for the most part, that works. So the main way that this works is by tracking two values for every placement group, both on the primary and the replica. One is readable until, that's the value on the primary. That actually no replica too, because you can do read from replica, but it's basically how far into the future we're allowed to service reads on data in this PG locally. And then there's this UB version, the upper bound, which is an upper bound on the readable until value for all of the other replicas. So how long any of our peers might into the future be servicing reads. And we maintain both of these values through these lease and lease act messages. So first, the primary sends a message basically extending the lease into the future, and that updates everybody's readable. I can't remember exactly what the sequence is, but basically you send a message to the replicas, they acknowledge back to the primary, and then the primary sends another message to the replica. And so basically once all the acting OSDs acknowledge that they saw the new upper bound, then the primary increases its own readable until. And so there's this invariant that's basically always true, that our local readable until is always less than the upper bound on all the clients. Or stated the other way, the upper bound that we have is always greater than or equal to the readable until on any of the acting OSDs. So it is truly an upper bound. And after that point, nobody is allowed to, not only us, but none of the other peers are allowed to read. And that's sort of the thing that lets us implement everything else. So that's
just a quick question. So the upper bound, it's not necessary that it'll be the primary or anything. It could be just any of the peers in the acting set.
Yes. So every replica, everybody in the acting set has an upper bound that is greater than or equal to the readable until for everybody else. Right.
Mm-hmm.
Yeah. And the replicas also maintain a readable until. So usually we don't read from replicas, but they have a value that they use if you do a read from replica.
Got it.
So that invariant works. The primary is driving the process by sending the lease ack, and then another lease message to make these update in the same way. But yeah. So the trick is that we have to deal with clock skew. So we're talking about timestamps into the future, and we have to deal with the fact that clocks aren't all aligned, and also they might be changing because you might be adjusting the time because NDP might be doing some annoying thing or an admin did something. And so all of this code uses a monotonic clock for everything. So monotonic clock starts, I think, when the system boots or whatever, and it increases monotonically. It never goes backwards. Even if you change the time, the monotonic clock doesn't change. It's sort of a monotonic local time, but it is meaningless on any other host because it's basically the time since it up. I think I can't remember. Whatever. I think it's implementation dependent, but it's only meaningful locally. So we use monotonic clocks throughout, and so all these timestamps are sort of like local only to the current host. And so the way that we share them between hosts is that we maintain upper and lower bounds on the deltas between any pair of OSDs that are communicating. So that happens in the ping code. When we this is the handle OSD ping code here. When we get a ping, this S is the session. So there's like a stateful object that we have between any two OSDs that are sharing pings, which importantly is anytime you have a peering relationship, anytime you have a PG that shares data with another OSD, you are sharing pings with those OSDs. So those are the OSDs we care about. So there's always a session object, and it has this timestamp structure. And we call got ping when we got the ping. That basically has our local monotonic time, and then the timestamps from the sender. And similarly, when there's an ACK ping reply, there's like a we also do it here. And those go to what is the structure? State structure here is heartbeat stamps. And again, so we're maintaining an upper lower bound on the delta between our local monotonic clock and our remote monotonic clock. And so anytime you send a message, then basically you know that it was sent in the past or at this instant, but in the past. And so calculate sort of the upper bound. And anytime you receive whatever, I can't remember exactly how it works, but you basically use this exchange of both the receiving the ping and getting the ACK, then you can calculate this bound. And the lower latency your network, the tighter these bounds are. So in practice, they're like, sub-millisecond. But if you'll notice that if you look closely at the logs, you can see these deltas get printed out as an interval brackets or whatever. Yeah, anyway, so that's how we translate timestamps between OSDs that are within the acting set. And so when we are sharing these lease messages, then we can use those to adjust. That mostly works, but there are also cases where we have to share timestamps with OSDs that we weren't already pinging, and that's when there's an interval change. The OSD map changes, and suddenly we have a totally new set of OSDs or whatever. And so in that case, you have all this information that goes into the pgHistory T. You'll remember pgHistory is the structure that has, it's got like all this historical information, like the last interval that was started, last epoch clean, all this stuff, name up since or whatever. It has some new fields now around, where is it? Prior readable until. So this is basically the timestamp for any an upper bound on how long a previous interval might have been readable. And so in general, if we aren't able, barring some other conclusion that we can come to, we have to wait until the previous interval's leases expire before we start processing writes, so that we don't allow a write to complete and then have some old OSD go process a read after that and then violate the read-write ordering. But because these intervals are shared with OSDs that we don't have the ability to translate timestamps in, this is actually expressed as just a duration. And so whenever we send one of these history messages, we basically say, oh, well, my upper bound is 2 seconds into the future from right now. And so we put 2 seconds in here, or it's 0.1 seconds or 10 seconds or whatever it is. So this is always expressed as a duration. That's obviously not super accurate because, who knows how long it takes to get to its destination. And then that 2 seconds is going to be like more than 2 seconds into the future when they add it to their time. But remember, it's an upper band, so it doesn't have to be perfect. As long as it doesn't travel backwards in time, then it's still correct. So that's sort of one sort of annoying thing. And there are a couple helper functions down here that basically this is called before we send a message, where we have the local OSD's current monotonic time and its upper bound, and we either calculate what this new duration is, or if the upper bound has already expired, then we zero it out because they're readable until the old lease has expired, and so we know that the previous interval is no longer readable, and we can move on. And similarly, if we're reading the value, then we need to add it to our current time in order to get sort of the local notion of what the prior interval's readable until is. So those are timestamps, which are mostly annoying, but they only sort of crop up in a couple places, so we can mostly ignore them. All right, prior intervals are expressed in terms of this duration instead of an actual timestamp. Then there are two new PG states that we introduce. So the laggy state happens if the PG is active, but for some reason the leases aren't getting renewed fast enough. So we're active, we're servicing reads and writes, but for some reason we have a read come in and our readable until value is in the past, which means we're not allowed to service that read. In that case, the PG goes into a laggy state, all the reads get queued up, and until the laggy state is cleared because our lease is extended or something else happens, we don't service reads. But if the leases do go through because those messages make it through the network, then we requeue those reads and then they get serviced. So that's a laggy state. Mostly, you really shouldn't see this unless your lease interval is like too short and you have like a slow network or really heavily loaded OSDs. So most of the time, this doesn't happen unless like the cluster's stress. Or if you have a partitioned OSD that doesn't know that it's not talking to the primary anymore, and so its leases aren't getting removed, or it's the primary and it's not being able to get response lease acts from the replicas because it's been partitioned. In that case, it will eventually go laggy. It'll stop servicing reads, and who knows what'll happen. I guess either it'll eventually get killed, or maybe it permanently is partitioned and it'll just get stuck there in this laggy state forever, whatever it is. That makes sense?
The requests that were queued on this laggy OSD,
Mm-hmm.
what will happen to them? Will they come out without? How would they be reordered?
They will block there forever until the laggy state is cleared, or the OSD or the PG reappears. All those queues get dropped entirely. So in general, if there's an interval change, then all the requests on that PG get dropped, and the OSDs or the clients resend them. So in this sort of like, say the OSD actually was partitioned, they would basically queue up until eventually the OSD finds out that the OSD map changed. And then it would drop them on the floor. Or if there's like a short-term partition, maybe its network cable goes down for like whatever connection goes down for like 5 seconds and then comes back up. It'll go laggy, network will reconnect, all the messages will go through, the leases will get renewed, and then all those read requests will get requeued. There's a function in I forget exactly where in the PG code that is responsible for requeuing all of the blocked requests. And there's a very delicate ordering there because there are like 10 different reasons why requests can block, whether it's waiting for recovery or it's read leases or peering or whatever, all these different things. And so there's some tricky ordering. And so the read leases are either the lowest priority or the highest priority. I can't quite remember. They're in there somewhere. But it's all handled within that same function that does it. Right, so that's laggy. So that's an active PG that gets laggy and then comes back to life. The wait state is a little bit different. That's the case where the PG is repeering and the prior interval upper bound is still in the future. So we just have to wait. Peering is complete, and we're all ready to go, but we have to wait before we do any reason writes until the past intervals has timed out for the old leases to expire, and then we continue. So this one is probably a little bit more common, although in practice, generally ideally we don't see either of these. But again, also if you're in the wait state, you block the request until the timer expires, and then you just proceed. And so the trick is basically to hide this so that it never happens and users don't actually notice. And so with laggy, basically the PGs are sending lease back. The primary is sending lease messages if the PG is idle, or possibly, I forget if I implemented it or not, it can piggyback lease messages on existing messages. And so there's sort of like a free, without having the additional network overhead, there's sort of free renewal releases as other stuff happens. And in the, during peering is the main thing where, like, if an OSD goes down, the lease interval is always shorter than the heartbeat timeout. And so if you have to sit there and ping an OSD for like 10 seconds before you decide it's really dead, then the lease would have timed out at 8 seconds. And so the lease will have already expired by the time you move on, and you don't have to wait for it. The only problem is OSDs don't always fail by timing out. Usually, like the process, or often the process dies, or you stop them. And in those cases, we don't want to have to wait 8 seconds or whatever that heartbeat interval is. And so for that reason, the OSD map has new fields in it, starting in this dead epic. So this is like more extra stuff on a per OSD. This dead epic field is added in Octopus, and it basically says that this is the last epic that we were confirmed to be like completely dead. Like the process is not just that we can't reach it, but that it's like known to be dead because we killed it or something. Like we know it's dead. And the main way that we conclude that is there are two ways. One is that the OSD can send the mark me dead message to the monitor and like explicitly say, I stopped responding to requests, go mark me dead. Currently, no code path exercises that, although that's the thing that we need to fix. That discussion we had the other day, we need to fix with the fast shutdown, notify mon or whatever. It needs to send the dead message and do that only after it stops responding to requests. That's one way to do it. The other way is if we have a if you're sending a message to the other mon and the messenger disconnects and it tries to reconnect and it gets an E connection refused, then there is a callback from the messenger called handle refused, which is triggered if you get an E connection refused. And basically the underlying assumption, theory, whatever, is that if we try to connect to a process and we get connection refused, that means that the process is dead. Not that it's like the network's disconnected and it's not responding. In that case, we'd have a timeout or something. But if we really get connection refused, that means we can reach the remote host and that process is not bound to that port anymore. And so therefore we can assume that the process is really dead. And in that case, then the failure message that we send to the monitor has this flag that says immediately mark this OSD down and mark it failed, and that triggers that dead epic to be set. And so we can immediately conclude that that OSD is truly dead. And then later in all the peering code, when we are calculating that prior readable until upper bound, we assume that that OSD is dead and we don't have to wait for it, which I can look at here in a second. So far?
Yeah.
So readable until is sort of the keyword. That's all this code. You can pretty easily find it just by grepping for readable until. So this is the history T. You'll find this the prior readable until. This is the duration for any known prior intervals how long we need to wait. There's like a case here where if we have one history and we have another history that we get, there's this merge function that basically, in most cases, it just takes the max of the two. But the logic for readable until is a little bit subtle. So if we're learning about a newer interval, then the readable until might be our old readable until doesn't make any sense because it's for an earlier interval and we're learning about the interval that came after that. And so we just take that value. Or if we're learning about, we're getting a history from the same interval, then we can take the upper bound of whatever those two readable untils are. And yeah, we saw this already. This abbreviation is used in a lot of the debug output. It's the RUUB, readable until upper bound. You'll see in a few places in P, prior readable until upper bound. So it's like, it's a mouthful to say, but you can find it that way. The lease, these are the lease messages that go back and forth that they have. Yeah, these aren't. Lease ACK, that comes back. State. So in here we have, these are sort of all the peering values. So readable until, this is the local notion of how far into the future the current OSD is allowed to service those reads, and the upper bound for anybody else in the acting set. So this gets fed into the history. If there's like a peering process, we want to pass around the upper bound and make sure we wait for whoever the furthest future reader is. But locally, we only that value. This is the value from the primary readable until. There's also this set here, which is the prior readable down OSDs. So if you go into, so whenever peering starts, we build a prior set. These are all the OSDs that participated in prior intervals that we need to go query to make sure we have all the latest state. So in here, there is so on new interval, this happens just after we've calculated the prior set, feature bits, all this stuff. And we sort of reset all this stuff. So the bound for the previous interval is a max of whatever we thought it was and the current interval. So that's sort of our local notion of when we think that is. And we can update our history value based on that. And we print it out and we reset the list of down OSDs. But then we go through and we do the peering prior. Okay, so when we start, this is when we first start peering, when we do the scan info, we do the build prior, and then we set the prior down OSDs to all of the OSDs that were in the prior set that are now down. And the way that the prior set is built, it has both a list of alive OSDs that we need to query and also a list of down OSDs that might have useful information that were in those prior intervals but are now down. And so those are the ones that we care about, right? Those are the ones that previously might have been a replica or a primary, might still be servicing reads that we need to make sure that we wait for those to expire. If there aren't any, then we can clear the prior readable until upper bound, right? All the OSDs are still up. We're going to talk to them during peering, and so they're all going to find out that the old interval ends before the new one begins, and so we don't need to worry about it. But if they are still up, then we put them in this set, and these are the ones that we need to wait for. Then there's this check prior readable down that happens when we have an OSD map progressing, and this is where we look for these dead OSDs. So we look at all the ones that we're waiting for their releases to expire, And if the map says that they're dead, then we erase them from the set. And if we erased any, then and we're done. All of them. We aren't waiting for any more. Then we now know that we can clear the previous interval because all the previous ones that we were waiting for are now dead, and we don't need to wait for them. And this prior readable down set is empty, and we're good to wait. I think there's one other place where this pops up. Where is it? So it's this. A recheck readable. So if we called that function and it returned true, which means that we were unreadable before, but now we are, we can do recheck readable. Probably the thing that will requeue old requests if they're yeah, this is a thing where if we're not in the wait or laggy state, then it's fine, nothing's new. But if we are in one of those two states, then we have to go requeue. We can clear the PG state or the laggy state and requeue the waiting for readable requests back to life. And then so when we're activating, when the primary is going active, it's about to send this PG info to all the replicas. So it refreshes the duration in that history, PG history, because remember it's a duration based on the current timestamp. Monotonic now and the primary readable. So it does that before it shares it. Same thing, anytime it shares PG info, we always refresh that duration before we send it out. Oh, there's update history. This is the last, I think this is the last main one. So whenever we're peering and we get a history from a remote node, and this is called in a bunch of different places. So we call update history when we get for a primary and we get info from a replica, or for a replica and we get info from a primary, or for the new master, whatever. There are a bunch of places where we update history just to make sure this history is always sort of an upper bound of what's going on. In any case, in that function, we update our own history so that it has an accurate relative timestamp, and then we do a merge of the other history with our history, which basically sort of, I showed you that earlier, we take basically the upper bound, unless one of them is the new interval and it's expired or whatever, then we can just reset it. But sometimes we have to advance that history. This is unrelated to the releases. But this here basically is, if we do this, if we've updated our history, then we refresh our prior readable until upper bound by reading that value out. And we print out a nice message to say if it expired, just in case. So the debug messages are something to actually understand. I think those are the main pieces. I was thinking it might make sense to look at that recent pull request that's open, just because it touches one subtle piece of this whole process. So explaining that will make sense. Let me find the window. Here it is.
Yeah, I think that makes sense. I think I also have the link to the PR.
Yeah, here it is. It's 44015.
Yep.
Later, this was a couple days ago, so I had to refresh my memory. Okay, so basically what was happening was previously, I showed you this bit of code here where when we start peering, we do the build prior, and if there are no readable OSDs, then we clear the readable upper bound. I actually just showed you that in my code because my checkout here is a little bit out of date. That isn't quite right because it sort of relies on this inference, right? The idea is that if there are no down OSDs from the prior interval, then during peering, we're going to talk to them. We're going to exchange all these info messages and gather logs and all that stuff. And as a consequence of doing that, we're guaranteed that they have the latest OSD map and they know that they're not still readable for prior intervals. They know about the new interval, and so they won't service old reads and before or after the new primary goes active, right? But that's an inference about what's going to happen in the future, and so we don't want to clear the prior readable until yet. If we clear it right away, then it could be the case that peering doesn't complete, but our local value of history, of the pgHistory, reflects that the prior interval is no longer readable. Some new peering process starts, and maybe now there is whatever. We basically shared information that wasn't really true because we haven't talked to those other OSDs yet, and we don't know that they have seen the latest OSD maps and that they're no longer servicing reads. So this was basically a premature conclusion that could, in some weird convoluted way, lead to a wrong conclusion. So the patch removes that. And instead, we don't do that until we're activating. So it's only when we're activating, if there were no prior down OSDs, then we clear the readable until, and then we refresh the timestamp, and then we share it, we activate. So that was the fix. The reason why, I'm trying to remember exactly what the scenario was where this happened. So this came out of that thread on the email list where people, they were starting an OSD, and when the OSD came up, it was going into the PG wait state, waiting for prior interval to time out. And it was kind of a subtle, that was sort of a secondary effect of this underlying bug, because of the way that the code in that update history function was behaving. And it's probably not worth explaining exactly what the weird convoluted path through the code was before, but basically we were clearing it too early, and it led to some other confusing effect. This was the original pull request that added all this stuff, so it's broken down pretty clearly here. So we had to, we add field to the history, we add these PG states. This is an accessor that basically, the new version actually is slightly different to this, because so you can set up pool property, but it basically tells you what the release length is going to be. Yeah, here. But now we have the release length. So either the pool property is set and we use that pool property as the lease length, otherwise we multiply the heartbeat grace times that lease ratio. There's some stuff to set up the monotonic clock that we use extensively, the lease messages. There's some tracking numbers to keep track of leases. Quite remembering how that worked, but yeah, these are all the fields here. I think, I think these are used when we're sharing leases. So basically, let's see if I can stretch this up. We basically have a broadcast, a gather, and then a broadcast again, primary to the replicas. And we need to, at the end of that, we need to both increase our local readable until and increase everybody else's upper bound on what those values are. And it basically involves the primary remembering when it sent the original message, lease message, because there'll be some time before it comes back. And then when it finally shares what the new upper bound is, it has to keep track of some things. Same thing with the primary or on the replica side. So that's the infrastructure for that. There's some stuff so that we regularly send out these PG lease messages, then the process messages. We regularly send those out, unless we're piggybacking them on something else, which happens sometimes, but not always. We have to schedule those. We make operations wait if the PG is laggy because our leases aren't being acknowledged. And then the stuff around history that I just talked about. And then what else? This is a test. So there's a unit test in here. There's a Ceph test, OSD stale read, that's been around for a long time. This basically turns it on. This reproduces the bug, the original issue. And this adds it to the QA suite. This stuff adds the dead epoch information and basically has that optimization so that if we know that an OSD is dead, then we don't have to wait for at least the timeout. And then there's the document that sort of summarizes the high level stuff. Yeah, that's it.
I have a general question. So, like, when the PG goes into active clean laggy or active clean wait, essentially you're not able to read or write to it, right? But we do have an active in the PG state. So the assumption behind this, I'm guessing, is that this is such a momentary state that users will not even notice it. So that essentially the PG is active from their perspective.
Yeah, yeah. I mean, it should be short. Like it'll
Yeah.
generally only be a couple seconds, if that.
Mm-hmm.
And I think active already meant so many other things within the context, whereas and this laggy and wait states are only just pausing client I/O, but everything else that's happening in the OSD is free to happen.
Okay.
So that's why it's layered on top of active, a sub-state of active instead of some intermediate state before we go active. Well, the laggy has to be a substate because you're active and then you add laggy and remove it. Like that can be if you have like a laggy cluster, then that would be flapping. Or if like your lease intervals are too short or something and the messages don't get passed around quick enough, then that might happen. But the wait one, it seems simpler to do that than to make it a sort of a intermediate state before you go into active.
Yeah.
I don't remember exactly why I decided that, but that seemed to work.
Yeah, so I guess in general, when users do see these two states, the idea would be to look at the readable until, make sure that it's really laggy or really in wait state, and start like the first thing should be like if there is really a laggy network like you described earlier, right?
Yeah.
Otherwise, yeah. Okay.
Yeah, I mean, I think trying to think what. I think the state that they were mostly seeing, well, the second part, which that bug I went over fixed was when the OSD starts. And it was actually the wait state because that's we finished peering, but we can't start doing IO yet.
Yeah.
That's the one they were seeing. And that was due to this bug. I think in general, you would see that if somehow your OSDs aren't getting marked dead, they actually die. So if an OSD like is timing out, although that shouldn't happen because the lease is shorter than the timeout interval, but or if you did Ceph OSD down, Ceph OSD down 1, 2, 3 or whatever, where you just update the map and you say this OSD is now down, the OSD is still alive, right? It's still, and it may or may not get that OSD map update for some time, and so we have to wait for its peering stuff to complete. And because it's marked down, nobody's going to try to talk to that OSD. And so we have to wait. And so in general, with this stuff, saying Ceph OSD down on an actually live running OSD is going to lead you to PGs in this wait state. It's actually better to go kill the OSD, kill -9 or whatever, and then all its peers will get these connection refused, and then they'll update the OSD map if it's down and dead, and then peering can like fully complete and go readable immediately. That's actually a less intrusive way to do update or take an OSD down, which is maybe non-intuitive.
If I understand correct, Sage, if it is stuck in the wait state, instead of marking it down, better restart the OSD. I mean, if it is there is any way, a chance where it is getting stuck to wait state.
Sorry, say that again.
So what I'm asking is that, let's say if PG somewhere, because of some reason, PG is active plus clean plus wait,
Hmm. Yeah.
and if it is getting stuck in this one, instead of marking it down, most of the time, let's say if PG gets stuck in peering state, what we do is go ahead and we just say Ceph OSD down, and it comes out of the stuck peering. And so instead of using in this, better to restart instead of marking it down, right?
Well, I think you generally shouldn't see a PG stuck in the wait state because the
Okay.
wait state has a time bound on it. You're waiting for the lease interval, and that's usually like, I think if the heartbeat timeout is 20 seconds, then 0.8, so it's 16 seconds. Like at most, it shouldn't be in wait state for more than 16 seconds. And in general, it'll be less than that because peering took up some of that time. And the leases probably weren't renewed like the instant before interval changed. Um, but if you see any PG that is actually stuck in the wait state, that probably means that one of the primary OSD is stuck for some other reason, like just like any other
Yep.
peering issue, like something's making it not respond, or more likely it's just not responding. It's not reporting up to the manager very quickly, and the manager is overloaded, and you're just seeing stale
Yep.
PG state, something like that. Trying to think. This might be worth looking at. Let me share this really quick. This is this last thing. So this is the test that reproduces the issue. So basically, we have two Rados clients. So the first one connects. We create a pool, and we create a pool and create an IO context for it. And then we have a second Rados client. We also connect and create an IO context for it. Client one, we write the object. We make sure two can read it. That means that everybody has the latest OSD maps. Everything's all good. Both clients are happy. We figure out who the primary OSD is. And then we have this fence OSD function, which basically does an inject args on that. That's these flags in the messenger that basically make all OSD and monitor message get dropped on the floor. So that OSD is like no longer talking to any other OSDs or monitors. They're not. So basically, they're not going to get the OSD map update. So the old primary is no longer going to get updates. We mark it down, which means all the other OSDs are like, oh, okay, so now we can repeer with the remaining replicas, and we'll continue, right? And our first client goes ahead and waits for the latest OSD map. So it finds out about that OSD down on our first client. The second client hasn't gotten that OSD map update because it hasn't been doing any IO, nothing's happening, whatever. It should still be able to go and read that same object from the old primary, right? Because the old primary, it's still accepting client messages. It doesn't know it's down because it's in black hole. So client 2 goes and reads the object. Meanwhile, with client 1, again, we go and we write an updated version of that same object, new OSDs, and then we go back to the client 2 talking to the old primary. We read it again, and we make sure that we see the new data. So previously, before all this infrastructure was in place, that old primary would continue to service reads, and this would be 1. It would get the old value. And this, in fact, would be reading from the new OSDs with the changes. Yeah, so with all the release stuff in place, this will actually block for however many seconds before, and this will read it from the new primary. But previously, it would read from the old primary. But in any case, this used to fail. Basically, we would get 1 here, and we would get a crash. But now it all works. The comments are a little confusing because this test was written before it was fixed, and so they're describing the old behavior basically, and not the new behavior. Yeah. All right.
Oh. Yeah, I was just reading through the email thread on Ceph users. So the laggy state that they saw was not because of the real bug. It was just they didn't have the fast shutdown thing enabled. That was completely
Yeah.
two different things
Yeah.
going on.
And it was, if I remember correctly, it was actually because their require OSD release
Yeah,
wasn't set,
yeah,
and so they weren't
yeah,
encoding the dead epoch
yeah,
VMAP, and so it was always waiting for previous intervals. But none of that dead OSD optimization stuff was working because it wasn't in the OSD.
Oh, this is awesome. Any more questions for Sage? Anybody? If not, thank you so much, Sage, for doing this.
All right.
I at least know much more about releases after this. So thank you very much.
Good.
Yes, yes.
All right.
Thanks.
Thanks, everyone.
Take care, everyone.
Bye-bye.
Bye.